Welcome to The Debate. Right now, to save the planet from catastrophic warming by 2050, mathematical models tell us we need to do the impossible. We need to, essentially triple our global nuclear energy output.
Right, which sounds incredibly clean on a spreadsheet.
Exactly. You calculate the carbon budget we have left, you draft the blueprints, and, well, the math works.
The problem is, I think we find far too much comfort in those blueprints. We desperately want to believe that if the math works on paper, the physical, messy world of pouring concrete and navigating geopolitics will just naturally fall into line.
And that gap between the theoretical, mathematical necessity of decarbonization and the grinding reality of building immense physical infrastructure, that's exactly what we're tearing into today.
Yeah.
We are looking at a central question: should nuclear energy be aggressively expanded to meet global energy needs and achieve climate goals? We are grounding this in recent data from the World Nuclear Association's 2026 report and the International Energy Agency's World Energy Outlook 2025.
And we're also pulling from an academic framework on teaching critical thinking in science. Because, true scientific literacy isn't about just memorizing the IEA's targets.
Right.
It's about poking holes in the assumptions behind those targets, asking what happens when a perfect theoretical model hits the friction of human error and economic reality.
Absolutely. And I should explicitly state that as part of practicing that kind of clear scientific thinking today, we are going to carefully define some of the complex terminology as we go.
Yeah, just to ensure the arguments are accessible to all listeners, including those who might be learning academic English.
Exactly. So let's lay out where we stand in brief. Looking at the empirical data, I argue that the evidence demands a massive, aggressive expansion of nuclear capacity. If we're actually serious about the net zero by 2050 scenario, nuclear is not a luxury. I mean, it is an essential, proven, low-carbon baseline.
And I look at that exact same data and I see a massive blind spot. While nuclear power undeniably produces low-carbon electricity, applying that structured academic thinking model means we have to evaluate risks.
Okay, but
The aggressive expansion narrative it glosses over severe real-world limitations. It ignores immense project uncertainties and the totally unresolved risk of radioactive waste.
well, I definitely want to talk about the waste, but let's start with the baseline math, because the sheer scale of the energy problem really dictates my position. I'm drawing directly from the World Nuclear Association's 2026 statistics here. Right now, we have roughly 440 operable power reactors globally.
Which provide about 9% of the world's electricity.
Right, 9%. But crucially, that 9% translates to over 20% of the world's low-carbon electricity. It is an absolute workhorse.
Oh, I don't dispute the output of the current established fleet.
But we have to look at what it's competing against. In 2024, fossil fuels still accounted for 59% of global electricity generation.
Yeah, that is a stubborn number.
It is. We are still burning mountains of coal and gas to produce over half of human power. So when the IAEA states we need nuclear capacity to hit 1,079 gigawatts electrical by 2050, which is essentially tripling our capacity, that is not just a proposal, it's a mathematical necessity.
I completely understand the mechanical need for constant power. But, if we're actually evaluating this scientifically, we can't just accept a 1,000 gigawatt target at face value.
Why not, if the math requires it?
Because we have to look at the physical friction. The aggressive expansion model assumes we can just seamlessly scale up, while totally sidestepping the massive vulnerabilities of the technology. We can't ignore the byproduct here. We're talking about radioactive waste.
Right.
And just to pause and define that phrase, naturally radioactive waste refers to the highly hazardous, dangerous materials left over from nuclear reactions that require incredibly careful long-term disposal.
Which is a perfect practical example of evaluating scientific risks.
Exactly. You cannot champion the immediate low-carbon benefit without heavily weighing a 1,000-year geological storage liability.
The waste is a serious operational reality, I'll give you that. But let's weigh that against the timeline of the climate crisis. I want to look at the urgency of replacement. I mentioned we were at 59% fossil fuels in 2024.
Mm-hmm.
If you go back to 2005, it was 66.5%. In 20 years of intense global effort, we shaved off maybe 7 percentage points.
Well, but global energy demand has absolutely skyrocketed in that same period. We're producing vastly more power overall.
Exactly, which makes the problem even harder. But it's also due to the fundamental nature of the alternatives we've been building. We rely heavily on intermittent renewable electricity sources.
Right.
And to define that for our listeners, intermittent renewable electricity sources are energy sources like wind or solar that do not produce power constantly. They only generate electricity when the weather cooperates.
Which is why the fossil fuels have persisted.
Precisely. Because they are intermittent, you still need gas or coal plants idling in the background to keep the grid stable when the sun sets. Therefore, scaling up a reliable, constant alternative is just incredibly urgent to actually turn those coal plants off.
But urgency does not instantly translate into operational reality. Look at the WNA's own data tables regarding future reactors. You want a massive expansion, right?
Yes, and the tables show it.
They show 309 reactors currently listed as proposed, which would theoretically give you over 285,000 megawatts. On a spreadsheet, yeah, your expansion is happening.
It's a massive pipeline of energy.
No, it's a pipeline of paper, because if you read the methodology in the WNA report, they explicitly define proposed as meaning the timing is very uncertain.
Okay, but
And let's look at the projects actually trying to break ground. The data reveals the profound grinding friction of building these megaprojects. Under their construction figures, several units are currently suspended worldwide.
such as Angra 3 in Brazil?
Yes, Angra 3 and OMA 1 in Japan. We are talking about massive upfront capital costs, supply chain complexities of pouring specialized concrete, and 10 to 15-year timelines. You cannot build a climate survival strategy on very uncertain timelines and paralyze construction sites.
Okay, the capital costs and the suspended legacy projects are real hurdles. I hear that. But I think you are judging the future of the technology by its most painful past. Let me draw an analogy from our other source material today. The work at CERN with fundamental physics and quantum computing.
Okay, I'm listening.
At CERN, to get a quantum computer to work, they have to maintain subatomic particles in a state of near-perfect isolation. If the environment fluctuates even slightly, the system collapses. It is an immense engineering hurdle.
Right, they are managing extreme physical volatility, moving from principles to solving real-world problems.
Exactly, and nuclear power faces a macro version of that exact problem. We're taking the most volatile physical process imaginable, atomic fission, and engineering it to be contained perfectly within human infrastructure. Initially, just like early quantum states, those projects were incredibly difficult to stabilize financially.
But the industry is evolving.
Yes, we are designing smaller, standardized, modular reactors. We are moving past the bespoke, infinitely complex megaprojects like Angra 3. Shouldn't we judge the technology by its current engineering trajectory rather than past suspended projects?
It's an elegant analogy, but it actually perfectly illustrates my core concern. Let's talk about the margins of error. When a quantum computer fails in a laboratory at CERN, a scientist has to reboot a machine, maybe rewrite an algorithm.
Sure, the stakes are contained.
Entirely contained. When a nuclear mega project fails or when a country mismanages its construction, you don't just get an error code. You get a $15 billion stranded asset or worse, a severe radiological event. We are not just scaling an algorithm, we are scaling the production of incredibly hazardous material.
I understand the distinction in stakes, but that brings us to evaluating the reliability of the technology versus assessing the systemic risk. I want to defend the operational reality of the current nuclear fleet, because the data tells a story of relentless engineering success.
You're looking at the historical performance?
Yes, the WNA report shows that reactor performance has improved substantially over time. Specifically, the proportion of reactors reaching high capacity factors has increased significantly over the last 40 years.
Just to be precise here, we are talking about operational efficiency.
Yes, and for clarity, let me define that. A capacity factor is the ratio of the actual electrical energy produced by a reactor over a given period, compared to the maximum possible electrical energy it could have produced if it ran continuously.
Right, so perfect 24/7 operation.
Exactly.
A high capacity factor means the plant is incredibly reliable, and the WNA explicitly notes there is no significant age-related decline in performance for these reactors over the last 5 years. These plants are running safely and relentlessly.
I don't dispute that existing reactors are operating efficiently. The engineers in places like France or Ontario are doing phenomenal work. But if we are applying critical thinking, evaluating evidence means asking, what are the limitations?
And you see a limitation in the expansion?
A massive one. Past performance in highly developed, strictly regulated legacy nuclear states does not guarantee future safety in a rapidly expanding global market.
Ah, you are concerned about the emerging nuclear energy countries mentioned in the report.
Exactly. Bangladesh and Turkey are currently constructing their very first nuclear power plants. Dozens of other countries are planning to enter this space. You need a deeply established regulatory body that isn't swayed by local politics. You need a robust national grid, vast sources of cooling water.
It requires immense infrastructure, yes.
We are taking a technology that demands near-perfect human institutions and exporting it into complex geopolitical arenas. That introduces an unpredictable, systemic risk to the globe.
I see the hesitation, but let me reframe this as a direct comparative risk assessment. If a critical thinker must weigh benefits against risks, how can the localized risk of a regulatory failure or radioactive waste mismanagement in an emerging market outweigh the established global catastrophe of burning fossil fuels?
Because I am not advocating for the continuation of fossil fuels. I am saying your solution introduces fatal complexities.
But continuing to burn coal is the practical outcome if we don't scale this. 14 countries in 2024 already safely produced at least 1/4 of their electricity from nuclear power. If 14 nations can manage this infrastructure safely, the question shouldn't be, is it too risky? The question must be, how do we replicate that success worldwide?
Evaluating evidence doesn't mean shrinking from a challenge. It means refusing to wear blinders. When we look at the history of applied science, pushing theoretical models into the real world always introduces unforeseen friction.
Unforeseen, sure.
The physicists at CERN who gave birth to the World Wide Web could never have foreseen the systemic risks the internet would eventually pose to global security and privacy. Technology scales in unpredictable ways.
Unpredictable, yes, but undeniably net positive for human progress.
Only because we constantly manage its vulnerabilities. When you ask how a localized waste risk compares to global climate change, the risk of rapidly expanding nuclear power isn't just about one barrel of waste. It's about severe economic destabilization for developing nations. It's about the geopolitics of the uranium supply chain.
But that supply chain is already functioning.
It is functioning under immense strain. You are tying the energy security of emerging nations to a highly sensitive process that is vulnerable to geopolitical embargoes and conflict. The systemic risk is far broader than you are letting on.
It is interconnected, yes, but it is deeply resilient. That exact supply chain generated 267 terawatt-hours of clean electricity in 2024 without a global collapse. Yes, global expansion carries risk. The construction timelines are agonizing, but climate change guarantees destruction. The math of hitting net zero by 2050 simply does not close without aggressively building upon the capacity we already have.
It is a profound, almost agonizing tension, caught between the math of the climate and the friction of the Earth. And I think that brings us beautifully to the conclusion of our analysis today.
I agree. Let's summarize where the evidence has led us. From my perspective, applying rigorous scientific thinking to the WNA and IEA data leads to a stark conclusion. The stubborn reality that fossil fuels still generate 59% of our electricity requires an overwhelming response.
Right.
The 40-year trend of high capacity factors proves nuclear energy is a highly reliable engine for decarbonization. Expanding it to meet the IEA targets is the most viable physical path we have to replace continuous baseload power globally.
And summarizing my position, true scientific literacy demands we look beyond the clean math of those targets. The leap from our current fleet to a net zero 2050 target is fraught with severe physical and institutional friction. Between uncertain timelines, massive capital risks, and the unresolved vulnerabilities of scaling radioactive waste management into emerging markets, the aggressive expansion narrative glosses over realities we ignore at our own peril.
Yet, despite our deeply opposed views on the scale of this expansion, I think we have found undeniable areas of convergence. We both fundamentally agree that reducing our dependence on fossil fuels is paramount.
Absolutely. And we both agree that the underlying physics and engineering of the current nuclear fleet are scientifically sound. We aren't debating the validity of atomic fission. We are debating the wisdom of its global application.
Right. And applying a structured academic thinking model, stating the theory, presenting evidence, comparing perspectives, and evaluating limits really deepens our understanding of complex global systems.
It definitely moves us past simple pro or con talking points.
It absolutely does, and I would strongly suggest that our listeners apply these critical thinking steps to the source material themselves. There is so much more to explore, especially in the wider applications of physics discussed in the CERN material, like how scientific principles lead to quantum computing or the birth of the web.
Because science is never just about the numbers on a spreadsheet. It's about how those numbers survive contact with humanity.
Precisely. We aren't here to declare a winner today or to suggest that one position is definitively correct. We leave it to you, the listener, to evaluate the evidence and form your own reasoned conclusion.
It has been an absolute pleasure to examine this with you.
The pleasure was mine. As we sign off, I keep thinking about those blueprints we mentioned. The math for a zero-carbon future requires a massive bridge. The targets are set and the water is rising fast. The question remains, can we actually pour the concrete in time, or are we ignoring cracks in the foundation that might bring the whole thing down? Keep questioning the evidence. We will see you next time.